Okay. Yeah, welcome to today's lecture on neural networks and deep learning. And after last time we got the basics of neural networks, and then you looked on how neural networks are run on GPUs. Today we want to get the next step into what are there different types of advanced architectures. So we have this basic MLP framework where we have a fixed size input, fixed size output. While this is quite important for a number of tasks, for a lot of real world tasks, of course, it might not be possible to represent everything as a fixed vector. And therefore, before we are diving more deep into the different architectures in next week with CNNs, TDNNs, RNNs, self-attention, and so on, and introducing them in detail, we'll try to have a bit an overview on how this all relates to each other, where these models are similar, where they're dissimilar, and so on. So we have a basic idea of what type of network structures most commonly is used. And then based on this, can in the next week look into how we concretely implement them, what are then the real calculations. And so this will be the main idea of what we are covering today. I hope it's not too abstract. I try to always give quite examples, but it should give you the high-level abstract view on it, where we can then dive deep into the details in the next week. So where are we currently? So the example of the standard classifier we looked into in the introduction lecture was we have an input, and typically the input is a fixed size vector, an n-dimensional vector here in blue, which we get. Then we have the a neural network, and it generates again a fixed size vector, so an n-dimensional vector, which we can use. And if we want to train it, we said how we are training it. We're putting in an input based on our random initialization. We generate an output. We compare the output to the reference output, and then backpropagate and change our model so that it's more and more often will generate the same as the label. So our input is a fixed size representation, our output, and we need labeled data with input-output pairs to train that. So we'll look today into how we can extend that, but maybe the first thing to get things a bit more clear is even a fixed size representation is not super clear. I mean, yeah, if you have now one vector, you can easily generate or transform or predict another vector, but for a lot of real world problems, you don't have directly a vector. So the first question is, what is a good way of how we encode our input and how we encode our output? And we'll first do that now with a basic MLP, and then based on this encoding extended, and we'll see that we need more abilities to also address other problems. So let's look at a very simple example. Just imagine you want to build a weather forecast. So you somehow get some measurements, maybe today's temperature, yesterday's temperature, today's wind, cloud cover, rain or so, and then you want to predict what will be the weather tomorrow. Will it be sunny, rainy, or cloudy? So we have this data, and of course, in order to train that, you'll need exactly this data. You need pairs of input-output data, but here at least we can easily see how you can generate this data. You just record it over years, and then you try to do the prediction. But I mean, we can't put here temperatures in there and rain and so on. So the first question is, how do we put all this information we have into our vector? So how does this look if we not have like one input, but we have like a set of different features describing it of different nature? There can be numbers, it can be categorical values, and how do we then predict something like here? So yeah, let's start with each of them. So let's start with the input. So what input do we have? And we said we have today's and yesterday's temperature. So something like 25 degrees, maybe more the summer, and yesterday was 23 degrees. Then we have a wind, which says like a bit like how strong the wind was. It might have been cloudy, and the rain was 0 millimeters yesterday. So that could be some of the data you have. So the question is, given this data now, how do you put things into the neural net? So the first thing we have is numerical values. And this is quite easy. It's one dimension, and you can put it in. However, these networks typically work better if you somehow normalize them. So often we are not directly putting in the numbers. We normalize them somehow to be between 0 and 1. So you take your minimum value, your maximum value of your data, and then you do the normalization into the span of 0 to 1. Is quite easy. It's x minus x min divided by x max minus x min. And you have normalized your data. That makes it easier to get different types of input. They're all treated the same. Now, it doesn't matter if it's temperature or wind or so, they all will be more similar distributed. It might be easier to learn things than when you have some very high values partly and very low values somewhere else. Based on then, your temperature is like 0.75 and 0.716, and your wind is 0.06 or something like that. So at least for the numerical values, this is quite easy. We have now 3 values, and we can just concatenate them. We have our first 3-dimensional vector, and we could use them. Of course, it's important now, you always have to put them into the same order. So the temperature of yesterday should be always index 0, so that you always do exactly the same thing there, and you're not changing things. For categorical values, it's there's also one typical thing. You're just doing this, what is referred to as one-hot encoding. So if you have n possible values, that means you have one dimension for each value. So for example, if you have some of values from sunny to very cloudy, so 1 to 5, then the 1 gets into the vector 1, 0, 0, 0, 2 gets into 0, 1, 0, 0, 3 is 0, 0, 1, and so on. So always the 1 is at the index. The length is always 1. And you have now also a nice vector describing. You have now, of course, there is already a difference. So the numerical values you have described by a single dimension. Here you have multiple dimensions. However, this just means there is a bit more weight on that, but that is typically no problem in dealing with this. Of course, it already also tells you something about the numerical values. What restrictions do we have here? Does anybody? If you have the number of classes, if you think about that. So they have to be fixed. It's not like that you can like later, oh, there is a new class and you say, oh, now we introduced a very, very, very cloudy weather and it's a 6. So you can't deal with this. So if your vector is always 5-dimensional, now you can't make it 6 or so. So it has to be clear like what classes you have. With cloudiness, it might not be that problem, but if you think about like objects or so, you have to predefined number of objects. So if this is you can only like input the objects you have and not like any type of new objects or something like that. And yeah, with this is then quite easy. The nice thing is with neural networks, you can easily put in more and more information. The only thing you do is you concatenate all inputs. So we have the today's weather in green, yesterday's weather in dark blue, light blue wind, then cloudiness in like purple, and then yellow, the rain. So you just concatenate all together, and that's the nice thing. If it's all about numbers, you can just put them all together. So one big advantage of that is easy to add more information. The good thing about more information is that in general, it means you have more things to learn from, so you can do better estimates. So if you now get a new information which is helpful, I don't know what other like like how dry it was or something like that. You can just add all of these things to there. Maybe the date is also important, so you can just add the date in there. So it's straightforward to add just more and more information in there. That's not a problem because all of them are just numbers. You can concatenate them and do your prediction here. So the way of doing the input is in that way quite nice, that you can really mix very different types of information and generate then your one type of vector which does your prediction. The other question is the target, and there we can do exactly the same thing. So in this case, we want to predict 3 different types of tomorrow's weather. It's like rainy, cloudy, or sunny. And we can just do again a fixed vector. We do the one hot encoding of that. And then we have our type of neural network. So you have now clearly defined how your input looks like, how your output looks like. It's like a 5, 6, 7, 8, 9 or so dimensional input vector, a 3-dimensional output vector, and based on that, you can have any type of neural network in there and learn the model. So this is for this type of task is all we have to do. In mind, of course, also the output can have different values. So we could also have something like tomorrow's weather is 27 degrees. Then we have just 1-dimensional output, which is now a number and not like categorical values. And then, of course, it might make sense to again normalize it because the prediction is working better on like somehow a dense thing than like very widespread. Also, learning is then normally more effective, so we can do the same thing there. And the important thing of neural networks, it's not now. There's nothing really specific. I mean, the only thing that is specific is the how you encode your input and your output, but everything else can be done. So you can do a similar thing if you do now an object detection. So imagine you have an image and you want to detect whether there is like a cat or any other object, like a fixed set of objects. You can also put in your image here and do the prediction. We'll see, it might not be the best opportunity, but it's one possibility. So you rescale your image to have a fixed size scale. Then each pixel has 3 values. So in total, you have like 3 times n times m possible parameters. And then you can maybe normalize them also. You put them linearly in there. So maybe this is the first row, second row, third row, and so on. And this is your input vector again, which gets as input your image. And then you can have a fixed size of classes, maybe something like cats, dogs, humans, cars, or so. You have your fixed number of objects, and you can, in training, put your up there, like what object it is to learn. And then you can do prediction and predict this type of output layer. How would your prediction most probable look here? Would you also predict only 0 and 1s, or what would you do? Would you see if you use our activations functions from last time? Yeah. Yes, so it would be like just probabilities here between 0 and 1. Now it depends if it's like a single class prediction, so you have only one choice, you would use a softmax activation so that the probabilities sum up to 1. If it's like a multi-label problem, so that in the image there can be cats and dogs, then each of them would be a probability that this object is in there, and you have a probability for each of them. But you can easily encode them there, and we would have it there. Similar thing could be something, for example, if you have speaker identification. So imagine you have a very short sound snippet and you want to tell who is speaking there. You have a fixed number of speakers. So you have a speaker ID, you put that up there. Here down, you put now somehow your wave file, your waveform in some encoding, you put it in there, and yeah, everything does the same. So you will see we have very different types of we have very different types of like problems here, and once we have encoded them into vectors, they are quite similar in some way, and we can always use our machine learning. So are we done? Can all problems be like transferred into this fixed size representation there, and then it's done? And also, it's not only can they be done, it's also, is it useful? Or there might be sometimes challenges which are not really nice encoded here, and you mainly make your problem a lot harder if you encode everything like that. So the main advantage is we have in this feed-forward network, we have the same approach for very different types of models, and we've seen it's quite easy to integrate more information. So even a very different one, even if you think about the image, you could now add like some of the location where the image was taken off. That might be very helpful, but it's easy to integrate them, and the model will itself learn by its weights to focus on which part and which part is not so important. However, there are some challenges, and some of them I mentioned already. So one problem is it assumes really a fixed size representation. So, and in several problems, we have to deal with sequences where we don't have this type of fixed size representation. So if you think about a text, a sentence can have very different types of lengths. It can be, I like the lecture, I like the neural networks lecture, and I like the neural networks lecture very much. They are all not completely different. They're quite similar, but you see first, the length is very different. And also, like, if you would even like just try the most long, I mean, there is also some shift invariant in there. Like the neural network somehow is together and doesn't really matter if it's at second, at third, or at fourth position. It's somehow giving you often the same information. So yeah, just doing this type of feed-forward network might not be really the best way. I mean, more extreme is even if you think about the length of the recording. So a recording, of course, the length is a lot longer. You sample it, and you can say even the same sentence with different speeds. I mean, I can say, I like the lecture, or I like the lecture. I mean, the audio file will be very different lengths. It has exactly the same content. And so you somehow need to deal with this. And we need to be able to process also data, which might not always be the same type of lengths. Also on the target side, there will be the same question. So, I mean, we as humans, we are not like once trained and then we can only recognize the one and these types of objects. The idea is, can we also extend that? So if you once see a new object, you're then also able to recognize this new object, and you don't have to learn 50,000 other examples, but just by seeing one example, you can always see that. Or think about the speaker identification. Somehow in this way, you once train it, and then you can recognize the 10 speakers. That's not really what we want to have often. I mean, what you want to have is, if you then give the 11th speaker, you should be able to also recognize the 11th speaker. And for that, of course, we again might need a bit of a different type of network architecture. Then, of course, we should also like somehow understand the network, the input structure. So if we would put these three images as RGB, they are very different. So I mean, we said we are going just line by line. We are putting the pixels in there. And these images will be completely different because there is just brown on very different areas. So you would have to learn like 3 times that this type there is a cat, then this type there is a cat, and there. So you have to learn like at each position that this is a cat. And you cannot like once learn, oh, if 2 are next to each other, then it's like this structure somehow is a cat. So if you have to learn it individually for each position, that of course is not very efficient, and it's not easy to learn it. Because I mean, there is no real order in our representation. I mean, you could easily just swap everything. If you do that like deterministic, you'll have the same network. You're just multiplying each of them by a weight, and then you're adding up. So it doesn't have any information about the internal structure. It doesn't know that these two are mainly the colors of the same pixel, while these are colors of another pixel. So you have to learn all of that, which of course is very inefficient. So you just, I mean, as a human, I guess all of you wouldn't be able to easily see if you just see here 1,000 numbers, then like even if you like see it like 20 of these 1,000 numbers and you get this is a cat, and then if you get the next one, which is a cat at a different position, different numbers, you would not be able to say, oh, it's still a cat. It's like you see here these numbers that are indicating that this is a cat. And I mean, in text, it's similar. I mean, the walk is not always at the second position. It's always as a different position. But you're now somewhere learning that walk is meaning. In this type of network architecture, if you would just put the words always like at fixed position, you once have to learn what walk at the second position means. You once have to learn what walk at the third position means. You once have to learn what walk at the fourth position means. Again, it's not really efficient. It will not really learn very helpful things. So we might need to, build network architectures which are able to understand the shift and which are able to more understand, oh, this is walk. I first learn what walk means, and then I might integrate the context and learn that, oh, in this context, walk might mean something different than walk in the other context. And if you see that, we can extend to quite a different number of other model types. And what we want to look here is a very rough like categorization on how they are different and what they try to model. So the one thing we are looking into, what is our input? So it might not that we always have this one fixed vector. So we still normally always have vectors, but we might not have a single vector, but we might have a sequence of vectors. We might have in-dimensional input of vectors, so a grid more, or we have just a graph of network of vectors, and these are our inputs. So that is a one question we want to look, and we'll see that there are different architectures to exactly address this. Another question is the mapping part. So what is then our output? So if the input is this structure, how does the output look like? There are network structures which do a one-to-one mapping. So if your input is a sequence, your output is a sequence. If your input is a graph, your output is a graph. That is, of course, somehow the easiest. That was what we currently have. Our input is a fixed size vector, and the output is a fixed size vector. So one-to-one mapping. But you can or you need also models which do some type of pooling that can be locally, so that you're like shrinking the size of your input object, or like even globally that you have then like shrink everything into a fixed size representation. But as for the input, we might also need generation. So in the output, you also want to maybe generate other type of structure. We'll mainly focus today here in this description on generating like sequences, but of course it can then also be extended. Can you maybe generate n-dimensional inputs and so on? And it might be that we are not really interested into a classification, but like a lot of things can be also nicely modeled more on a comparison basis. And one difference which is also there is how you deal with data, what data you have. And we'll look there into prediction tasks, autoencoding, and GAN today. So that should, you see already, hopefully, this is a very high level overview, but it should give you a bit of intuition where we are diving into and how we can extend. So the main idea is that, as I hopefully like have shown you before, is that just this simple idea of always one vector in, one vector out is very nice for neural networks. On the one hand, you can do a lot, but you cannot deal all problems which are nice and which we want to deal in. So we have to somehow extend this to other types of models which can better handle these types of inputs, these types of function of mapping between input and output, and this type of data. Yeah, before we are going into this now, do you have any questions? Good. So let's start with the most easy thing This is what we have for the input. That is what we had before. Of course, this is an important use case where we have fixed size input and fixed size output. So this is one thing how you can do it. You can just take this input and map it to the output. However, it's not all we want to deal with. So another important size is we have a sequence of fixed size elements. So the length of the sequence is variable, but in this, it's important each representation we put in here is still a fixed size representation. So you can think of that like if you have, for example, words, you have a fixed size vocabulary. You said you have like 10 words or something like that. And then your representation here is always like a one head encoding of your 10 words. I mean, that's not realistic. So more you have like 10,000 or 100,000 words. So here each vector is like 100,000, but your network architecture should be possible to not only get one of these, but it can be two. And that's now the important. The same architecture should also be able to be handled with 3 or with 4 types of inputs. So we don't want to change anything up there. So even in training, if we have training only seen sequences up to length, like only 1, 2, and 4, we still want to be able also to deal with 3. So you as a human, I think it's no problem. You might have never seen a sentence with, I don't know, 251 words. But if you get one by random, if your ChatGPT is writing you a sentence with 251 words, it wouldn't be a problem for you. You can understand them. You don't have to train it all the time. And for you, you'll understand what walk mean. It doesn't matter if it's happening, if it's like at the 4th position, at the 3rd, or at the 2nd position. You know that, I mean, of course, walk might have different meaning depending on your context, but you can still apply this at all positions. And the same is, of course, happening for audio. So if you get audio input, it might be that you like, I mean, of course, audio is like somehow continuous. You might have heard about that. You have to like discretize that. So with some type of algorithm to get like a representation, but that signal processing can do that. And then you should also have like some vectors in there for each time step. So maybe that's an important point. Of course, we're still dealing only with discrete types of inputs in the length. So we are not dealing with like having, non-discrete inputs here, like at the time steps. But that is possible, but you should be able to get like different types of sequence lengths here and deal with all of them. So the question, if you now have that, how can you do that? And this will be, a large part of the next architectures, where we exactly look at architectures which can deal with this very type of input and handle them. And how can you do that? So you can have first a local view. So if you want to understand what this word means in a local view, the idea is we are now applying our network always on part of the overall input. So the idea is, okay, if we have variable length input and we can't handle variable lengths, what we can maybe do is always look at some part here and apply our network to that. Because on that part, it might be possible to have then a fixed size and we can deal with that. So what is then important, of course, is we still need the context. So in order to understand walk, it's important to see which words are around there. So we are trying to understand this one element in our sequence by looking at the element and maybe other inputs, which can be, for example, the previous and the last. That is the nice thing we talked last time. The nice thing about neural networks is we can easily add other context in there. So we can look at the current position and we can just also take the previous and the next and use it as input and handle it this way. So one possibility to incorporate your context is to add input again, as we have done before, to add other information. We can also add input to understand one position. We try to add the surrounding things in there. This is one major type of idea. There's another thing, and that is we try to incorporated learned representation we had before. So again, we have a local view. We always look at each element of it at a time. And now, instead of putting other like surrounding context into that other types of networks, they put previous learned hidden representations. So if this is our second position, we are learning some new hidden representation. It might be in order to understand this hidden representation, we put in our previous hidden representation, which somehow makes a more indirect influence of the input. So in the first step, the context is directly influencing our hidden representation, while now we are influenced via the other states. So we are first learning a hidden representation for that, and that goes into this step. But what is important is that you really do the steps. So from a local point of view, in order to deal with sequences, the common thing we're doing is that we are somehow applying the same network, and we'll see these networks are somehow similar to the feed-war at each position. And thereby, we are able to handle variable length input, because you can easily, of course, apply the same network, not once, but you can apply it 10 times. And there you don't need other types of weights. You can use exactly the same weights. You just apply them 20 times, and then they are like they're in, or like they're helping you to understand the context in that. And this was more the local view. I call it local view because many are looking at each element. So you're understanding what does these architectures, or how can we deal with sequences when we're looking at each element of the sequence. So you look at each element of the sequence, and you assign, then it's like somehow fixed size, and you're applying it. You can also look at more on the whole sequence side. So you can have it as a global view again. And there, what it means, all the ideas we had before, is that we're somehow have a network. And how do we get now a network which has different size? So that means our network here gets 3 inputs. It has, of course, to look different as if our network has only 2 inputs. How do we get that? We're just like do parameter sharing. So we're copying our network several times, and one processes the first structure, it secondly positions the second part, and thirdly it processes the third part. So you can either view it as, okay, each element is processed one by one with the same type of network, or you can view it as there's one big network, and that's always like specifically designed for your different inputs by copying the network at different positions. If you're like in this type, you would, for example, at each position take the context. You can also do the other thing, then it just looks a bit different. So if you're doing like the previous hidden state, that would be more like this type of network architecture. So the first input is used for your network, then the same network gets a second and your previous hidden state, and the third one gets the third and the next hidden state. So again, also whether you encode your context by surrounding hidden states or by surrounding inputs, in all of the time, you can view it in these 2 ways, that you either process it several times, or that you copy your network several times and have it therefore several times there. And what I described you at a high level here is then concretely implemented in quite a lot of different types of architectures. And here you see the next type of lectures. So this thing here is mainly what is done in a time-delayed neural network or in a CNN on the convolutional network. You're getting as input not only your current position, but also the surrounding ones, and therefore you're incorporating local context. The other thing with the hidden state, that's exactly how an RNN works. Recurrent neural network, you use the previous hidden states. Similar things are also done in self-attention. We are playing the same operation, but we are applying it even to all the states we're having. again, and somehow you can then like summarize everything. Or in state space model, always the idea is somehow you need to apply the same types of operation at all different positions, and thereby you can handle variable length input because you don't have to learn things. It has an additional advantage. So it's not only addressing the challenge that we can handle different length input, but it also, if you look at it more from the parameter sharing, it's a lot more efficient because you not have to learn now what walk means independently at position 1, 2, 3, and 4. But if you learn it at one position, because these information are also used at all the other positions, you're also, learning this in order to better understand that. Good. So this is for sequences. Any questions about that? Yes? Yes. So I mean, what I mean with fixed size element is each of these boxes has to be a vector which has again a fixed size. So it cannot be that this is a vector which has size 5 and this has size 4, because then you cannot apply the same network at all positions. But the length here is independently. Yes. Yeah, but I mean, they're used in forward processing. But also in CNN, you will have the same thing. So you have a sequence. This more looks like a CNN. You apply the same thing and look at the context. In an RNN, it's more like this step where you use your previous hidden state. No, this you can't do in an RCA in a CNN. So this CNN is like this. So that's where you use only the inputs to calculate RNN. But for the others, I mean, we'll discuss all the details in the next lecture, but you should get the overall idea that in all of that, you have the ability to process the like a different size lengths by just looking at each element at a time and applying the same operation there. It is, yes. I mean, then you just apply your CNN at each position. That is the important thing. I mean, that's why you can replace in any model a CNN normally by an RNN. I mean, it might have different advantages or disadvantages, but at least for like CNN I mean, that's only true for sequence processing. If you do more dimensional, we'll come to that. But in a sequence processing, you can have a CNN layer which gets as input a sequence of states, and here what you're outputting is also a sequence of state. And that is always done by an RNN as well as by an CNN. So the question is, can we also somehow extend that to n-dimensional input? And we already have done that implicitly a bit with a picture. So, I mean, one thing of doing that is of course quite easy. You can linearize that in a fixed size, and then you have exactly done that. So you're able to do that. However, if you just linearize, of course, you might lose information because I mean, now the connection, the relation between blue and, between green and blue is exactly the same as the relation between blue and red, which of course is not the case. I mean, blue and green are next to each other, while blue and red are like diagonal. And these are, of course, important information, which you should understand. Therefore, when you're doing that in your architecture, you like have to also encode this type of contextual relations. So we have encoded that for sequences, but there's only two possible relations. You can be to the left or to the right, at least from direction. Of course, you can be 2 to the right and 2 to the left and so on. Here you have a bit more possible relations, like that something is like up, down, right, and left. So if you go over it, you should somehow encode these type of relations in there and process them there. But otherwise, it's exactly the same thing. So now you just have a different type of structure. So instead of a sequence structure, you have now a 2D structure, and you can apply at least again the CNN. The RNN gets a lot more or gets a bit more complicated because you have a direction in there. So it's not always easily clear how to go. There are ways of doing that you have. I mean, in this way, you could see that you have always a left predecessor and a top predecessor, and you have two inputs. But yeah, the difference in 2D is really, or like then also in ND, that you have more relations. So before we had only the relations before and after, and now you have more dimensional relations. But otherwise, it's similar, and we'll see, for example, a CNN is a typical example, which you can use for one-dimensional and for two-dimensional, and they're used for both and have advantages in both. And with this now, you easily see, of course, you can extend that now. So if you think of general graphs, we have two types of graph structure until now. We didn't call them graph, but if you think about it, the sequence is like the graph structure we have up there, and then down there you have the grid typically of a 2D thing. So these are two specific graphs, and we have dedicated architectures to address exactly these type of graph structures. But of course, you might be, or you are able to extend this to any type of graph. So what it looks like then is that you have somehow this general graph, and then you as input, you somehow put in your current node and some information from your neighboring node. Of course, things might get a bit more difficult because anybody sees what could be more challenging in general graphs than in like the graphs we had before. Remember again about the fixed size information and which sizes are known or unknown. Yes, exactly. So in this type of previous graph, we either always have two neighbors, so we can always include these two or like some that, but it's clearly clear how many surrounding you have. And here it's also clear it's more. You can up and down and right and left, but it's still fixed. If you want to deal with a network which has, which is a general network, of course, is no longer fixed. So you somehow have to do some other type of summing them up or so to get a fixed context representation. But it might not be longer that easy how to incorporate that. But in general, you can apply similar techniques by just looking at each element individually and somehow encoding your context around it and applying it to that. So yeah, with this, we have somehow learned now different types of layers. If you think about it, what layers we had is, if we have the fixed size representation, we get one vector in, and we'll generate one vector out of that. If we are looking at the sequences, we get in a sequence of vectors here, and we're generating a sequence, and this sequence has exactly the same length. So it's like this one-to-one mapping where you have an input sequence and you generate the matching output sequence. For a graph, we can do exactly the same thing. We have as input some type of graph, and we're generating the same graph because we always, we're putting each image into like the same, each point into the same network. So we are generating exactly the same points up there. Whether that's now image points or anything else, we'll see. But it's like the structure is exactly the same. Your output is the same as that. And for graphs, you can do the same thing. You can do also like you input a graph and you get some input. So this is like the type of networks we looked from the input. So the question is now, if we have this type of layers, we can now do a lot of things, of course. But is that really all we need? Or it might be that we need more things. It might be that not all problems are described by the same input and the same output structure. Any suggestions with problems you can't solve here? Yes, exactly. So that we don't have. You have, I mean, then you can generate another picture of the same number of dots with this type of architecture. Which is, I mean, it sounds now crazy, but it might be an interesting problem. If, for example, if you think about segmenting, that's exactly what you're doing. If you want to know this is a car and where's a car and where's a house, you might like classify each dot as like this is a car, house, and so on. So it's a valid task. So there are realistic tasks for that. But as you correctly said, it might not be what we're really talking about. And therefore, in addition to this one-to-one mapping, we might need more. But first, have a look what we can do. So there is a lot of tasks which we can do and where we can apply this one-to-one mapping. So the nice thing is we don't need any additional type of layer around it. It has to be the same thing. There's one important thing. For each element, the number of dimensions can be different. So it has to be fixed, but it's not that the input and the output have to be the same. So even the initial example of our weather forecast, our input dimension was 9 or 10 and the output was 3. So we can have different numbers in there, but the number of elements have to be the same for each of them. So if you put in a 10-dimensional vector, then you get always a 3-dimensional back. And you can do that for weather forecast, but there's also other types of tasks. So there's, for example, also people are using that for sequence labeling. One example is part of speech tagging. It's maybe not so common. Maybe you can remember that when you were in school, you had to identify this. So if this is a sentence, I walk, then walk is a verb and I is a pronoun. So you have to like give a class for each word. If you want to do that, it's a one-to-one mapping. Each word gets exactly one class. So that's what you can learn and apply all the time. So there is a lot of tasks, or we have the semantic labeling where you have this one-to-one mapping, but of course it might not be everything we want to do. And therefore there's more things we need from model types. So one thing is you might want to do some type of pooling. So you want to reduce your structure. And that can be, first of all, a local pooling. So that means, for example, if we have a sequence of 4, we want to reduce it by a factor of 2. So we want also summarize 2 things to 1, and then again 2 things into 1. So there we are getting a representation up there, which is just more compact. So there's, for example, that if you think about audio processing, audio is very redundant. So you might prefer that you if you have a very long sequence here, and then you want to compress the information into a shorter sequence. And if it's done locally, this is, of course, might be, again, quite easy, because if you just apply the same network, always not at one position, but always at the second position, then you somehow have achieved that. So you shift by more or less, and we'll see that that's, for example, how you can do that. Or I mean, if the information are redundant on your input, you might also just remove some of them. So there's different ways of doing it, or concatenate outputs. But if it's a fixed factor, then this is, of course, always possible. Because again, it's mainly like, how you can view it is that you're not inputting each element individually, but you're always putting in them in groups of 2. So in all the previous models we have, if you put them in a group of n, you're downsampling your output to some size. And how you can do that? How can you like input into the models we had like 2 elements always at once? Any idea? So you have a vector, you have a vector. Now we somehow need our model which applies on each position. We have to jointly put them in there. So what are you doing? You just concatenate them. Then you have a new element, which is just joint element, and you're putting that at each position in there. And that's all you have. And we had already previously an example. You might not only want to do local pooling, but you also want to do global pooling. So that means that you want to summarize everything you have into one single, like, fixed hidden representation. That can be done for classification of images. Another thing is classification of text. where you want to do sentiment analysis or something like that. And then you need another type of layer on top of that. Typical things are, for example, what we'll see is like things like mean or max pooling. That's the easiest thing. So if you just have like 5 representations, you can take the mean of them. Then you have a new representation. It has a fixed length, and you have only one. And of course, information get lost by pooling. That's typically happening. I mean, you have less space to store information, but they might be helpful. Good. So this is now making things easier. So we have the first step was like keeping the same structure. Then this one was reducing the structure, either like to a fixed representation or by a fixed factor. But you might not only want to do that, but in a lot of tasks, you also want to generate a new structure. And we'll look into this mainly on the example now of text, for example, or sequences. So you might have a task where your input is some type of input, and you want to generate a new type of structure. So one example of that is what is now known as image to text or captioning. Just see you have an image here, and you want to generate a caption of that. So you want to say, this is an image of a cat. If you have that, now there is a variable length output. So you have like one vector for each word, for example. We had categorical values, so each one is maybe one hot representation. But the number of outputs here, I mean, is not easily to determine based on the image. You need the full network. It's not that you get an image and you always can describe it by 5 outputs. It might, I mean, for a cat, you write that, but for like a cat and a dog, it will be then 2 more words. So there's no easy correlation between them, which you can like predefine. But really, the model has to self-determine where, like, how many outputs you will have there. So you really have this type of generation process in the network where you generate different types of output. Another example of this is machine translation. So if you have an input as a source language and the output as a target language, here you're lucky, you have the same number of input and output words, but I mean, there is a connection between the number of input and output words, but it's not simple. So you cannot easily say, oh, we take this architecture. If there's 5 words in the output, there's always 1.76 times as many in the output or something like that. So it really depends on the content and on all your work, like how many output structures you predict. So we need, again, some type of different type of network structure to be able to not predict a fixed or like a mapping, but like a really completely new type of structure, which can tell us then what is the output structure here. So yeah, how can we do that, or what is the challenge here? And the challenge is we no longer have only to predict the content, what we had before. So we had to predict our vector, but we now also have to predict the structure of our output. So in addition to just predicting the individual components, we also need to predict our structure. Let's do that for the simple case. So the simple case is a sequence. And so the structure here means like, what is the length of the sequence? So you somehow have to predict, is your length output 3, 4, 5, 6, or 7 or something. And then you have to, like somehow, of course, once you have to predict it, your sequence, you have to decide what is each of these values in there. And for sequence prediction, there is one very successful approach of doing that, and that is autoregressive. And it's, again, the idea is, as for the input, if you have variable input, what we're doing is we are treating each element somehow at a time, looking at one, and then as a fixed size. So the same thing is here in autoregressive. What does it mean? So we are looking at our current state, and then we are predicting our first output. So we are predicting the first word. once we have predicted the first word, we are continuing until we're somehow predicting this is the end of your sequence. So when you start maybe with start, and then you do your first prediction, and your prediction is today. Now there's one important thing. You somehow have to tell the model that it predicted today. Do you can you understand, or do you know why it might be important to tell the model that, yeah, you just predicted today, because it might not know that it has predicted today? No, the thing is, again, what do we predict? I mean, you couldn't directly know. So the thing is, what do you predict? You're normally not predicting a word. We said these are categorical values. So what you predict is a probability distribution. Based on the probability distribution, then we somehow have to make a decision. We did it before also. If you predict the weather, normally an end user doesn't want to see tomorrow the weather is with 30% it's rain, with 2% it's sunny, and with 60% it's cloudy. What you will present to the user then, it's tomorrow it will be cloudy. And here is also like, you can't read, oh, the first word is with 5% it's today, with 3% it's yesterday, with 2% it's something else. So what you're doing is you're like taking this probability distribution and taking then the most probable output. So the model doesn't know that you took that. The only thing the model knows is, oh, it predicted this probability distribution. Then you select one element, and then you tell the model, oh, today is the next element. And now you have your sequence input. You can predict the next word. So this is now again the same thing as for the input. For the output, now we're generating our stuff word by word. We're now predicting again the next word and predicting, oh, the next word might be I. And then we're sampling I and telling the model again, oh, I is the next word. We're continuing this, like what did I walk? And then at some point you predict, oh, it's the end of the sequence. So the important thing is we need to extend a bit our vocabulary, not only to predict the words, but also to predict the structure. And also, in order to predict the structure, what we have to tell the model is, oh, there is an end of sequence. Now you again have a similar type of idea as we had before. So instead of like directly handling variable type output and predicting the overall structure, it might be difficult to directly predict, oh, the output has 25 words, because how many words it really is depends on what words you selected. There is work on that, like non-autoregressive model prediction, where you try to predict everything at once, but it's a lot more challenging. In the autoregressive model, you again have this trick. If the problem is too big, you sample it down and don't only look at one position at a time. You're predicting the first position, and then based on that prediction, you predict the next one, and so on. And this you can continue. Of course, there might also be one disadvantage of doing this type of percent. I mean, there might be several, but if you think about it, what could be a problem if you like predicting one by one and always just the next one? You think about the calculation time and things like that. Just think about what we talked about, CUDA and parallel processing last time. Yes? Yes. So that is a challenge here, of course. So you can only start processing today once you have predicted that today is the most probable one. So you go step by step, and you have to do the calculation from left to right. You cannot parallelize that. And like predicting long sequences might get, challenging them. Therefore, like to do this type of prediction, we typically can have this encoder-decoder structure. So the idea is, first we have an encoder which learns some type of structure that we had before, and then we have the decoder which does exactly this step, that is like reading in these things and predicting one by one. So this is a typical type of network structure we'll see again in this lecture. There's one other to-do sequence generation, which got more common, and that is exactly how a large language model look like. That's a decoder only structure. That means we have the same type of processing for the input and the output. So how can you do the same thing for the input and the output? The main idea is also like your input, you're just processing the same time, but you're not predicting, you're ignoring what is predicting. You're just reading this time, processing first word by word, everything that is your input, and then you're continuing by generating the output. And that is like, of course, a bit like how language models are there and are trained. They're just trained on text and predicting the next one. You're doing here exactly, always just predicting the next word. So this is a way of doing this type of structure prediction. Like at each position, you're just looking locally, what is the most probable next decision. Good. Any more questions to this type of generation of new structure? Good. So with this type of generating of different structures, we have now the advantage that we have we can generate different types of structures. So you can generate sentences of different lengths. But one problem is that it's only possible to generate like we said, each element in your sequence has a fixed size. So it's always like your vocabulary size or something like that. So you cannot learn like a new concept or something easy. So especially if you think a bit again about of your image recognition, so then it might not be the best way of doing it, because the once you trained it, you can recognize your 10,000 objects. But if now there is a new object which you would like to recognize, that is not possible. You cannot easily add some type of somehow new object in order to generate that. There might be some crazy idea of doing that. Any idea how you could do that now if you would like generate new structure or new objects? I mean, you could do like try to generate there the word, and words have like you can express every concept, mainly what we have in a word. So if you would do that as an image to text, it's so long that clear if it's fixed or not. But it might not be the best way, because you have to also understand what a dog is and so on. So in a lot of cases, you might also want to have the ability to that you can easily like add new types of concepts in there. I mean, another example is what we had before, the speaker identification. So if you have a new speaker, you want to easily recognize that this is a new speaker, or that these two are like samples are from the same speakers. So we cannot easily learn new elements here. It's the same thing we always had. We have the weighted sum, and only for the elements we have seen in training, we can learn that. So the question is, can we have somehow a different types of architecture which allows us to easily add new classes into there, and also learn new type of output classes? And there is, and that is what people refer to as theorem-based networks. And the idea here is that, instead of predicting something, we are learning hidden representations, and we are doing the classification then not by classifying or predicting the category of that, but what we're doing is we're comparing this hidden representation. And the idea is if there's dog and cat, the two representations should be dissimilar, while if it's the same representation, we try to learn them in a way that they have a similar representation. So it's like, instead of directly predicting this is the class, in this type of networks, what you are doing is you're putting in a sample and you're putting your thing you want to classify, and then you're looking like how similar they are. Because if you just measure similarity, you can then find the most similar one and somehow do this type of classification. If you have a new object, you just put in there a new reference, and then you can compare it to that. So what we have to do in our network here is now not to have an output layer. What we need to do some type of comparison. Any suggestion how you would do the comparison? So what we have is, I mean, this is a neural network. So in the end, we generated there a vector, and this neural network will generate there also a vector. If you have two vectors, how can you compare them? Yeah. Yes, so you can take, for example, the cosine similarity. That would be a very good idea, and that's commonly used. So what you calculate is the cosine similarity, and if you train your model well, then this type of similarity should be quite bad. So it should recognize these are two different objects. Of course, we have to think about how we can train that, but this is the idea. So you put in a cat, you get one representation. You put in a dog, you get another representation. And then you have two very different types of representation. In contrast, if you put in one dog and you put in another dog, hopefully you'll get the two things in and you get a similar representation. So your classification is done based on your similarity metric up there. And now you can easily add new objects. Of course, I mean, if you're two completely different objects, you might not be good in learning them because your representation is not good. But you should at least generalize to similar objects or something like that. Of course, you can save here some time if you think about that. Imagine you want to classify now this type of dog. Do you need to compare it to always calculate that? Of course not. I mean, you can pre-calculate things at some point. You just have an embedding up there. So you have for each of your objects which you want to classify, you have to store this type of embedding, so a vector representing them, which is learned. And then during inference, what you really do is you calculate for your new image an embedding, and you compare it to see whether it's similar or not. And then, of course, there's additional speed up, and maybe you can't do all the comparison. So then you have to have an efficient nearest neighbor finding. So you based on your new embedding, you want to find the nearest neighbor, the most similar object. You can then compare the similarity of the most similar object and see whether this is similar, and you say this is the same object or not. The important thing is here, we are no longer even restricted to a fixed number of we are not restricted to a fixed number of classes, because now, I mean, you can store in your database as many embeddings as you want. Of course, things get more complicated and so on, but you can easily add new examples and also be able to classify. The question is now, of course, what is your learning? I mean, before you were learning, we had the loss function. We calculate the similarity between the correct one and the one we are predicting. So if we have the categorical values, we predicted the similarity between 0, 0, 1, 0, 0 for the class and our prediction, and that was our loss, and we want to minimize. Can we do this here also? What might happen if you just, I mean, you could, of course, put in here your same images and you try to make your losses the difference between these two. Does anybody see a problem which might happen? If you, yeah? No, I mean, you're telling the model, oh, these are two the same object. You always give twice the same object in there, and then your loss is making these as similar as possible. Anybody has an idea what a good solution for that would be, where you would have a very low loss? No, it's even worse than that. It's going in the direction, I think, but it's even worse. So there's a very simple solution that you have here a loss of 0, that the two representations are the same. You can just even on the same thing. That's exactly. So if you just learn that you always map everything to 0, then you'll have a loss of 0. because the two vectors are the same. So just making them the same is not enough. In order to be a good classifier, it's important that these two are the same, while the other two, they should be different. That you also have to tell, that the objects which don't fit together, they should be as far apart as possible. And that is what people refer then as the triplet loss. So the idea is then your loss is that you're somehow, if you have your answer point, that's what you're trying to learn, that you're trying to go as near as possible to your positive. So these should be as similar as possible, while you want to be as far away from the negative as possible. Or at least you have here the maximum. So I mean, if you're a maximum away from them, that is also fine. But you should be some way away from your negative. So that is the idea, that you not only have to go as near as possible to one, but you also have to go far away from the negative ones. Because otherwise you have this collapsing that you're just learning a simple solution. And that's in generally something which is important with neural networks. Always think if there are some loopholes in there, and it's very easy to predict because the network will find them, and then it will not solve the task. So here you see, in general, the idea, yeah, we just make positive examples similar, is straightforward and seems to be right. But the problem is we can have an easy solution for that, but just making everything similar, and then the network is not helpful at all. Yes? Yes, I mean you can use it with generally with any type of distant metric. I mean cosine is an easy one, but yeah, if you have a fixed one, then you don't have to clip. Otherwise, it might be helpful to clip. So yeah, if we're looking at this, so in total, we'll have yeah, different types of mappings that we can learn. So we started with the most straightforward one, which is a one-to-one mapping. That can be done for a single input vector, then it's like our feed-forward network. But it can also be for more complex structures, then it's like RNN, CNNs, or any type of structure. So that is one thing where you don't have to do anything specific to your structure, but you're predicting exactly the same structure as you have in the input. Then you might want to change your output structure. In that case, what you're doing is that you are going, I mean, one thing you can go to a simple structure, either like a smaller version of your input, which is a local pooling, or to a fixed size representation, which is global pooling. And a lot of things, if you think about classification, any type of data, this is typically what you're doing. Then there's generation tasks where you want to generate a new type of structure, and that is not, they are directly connected to your input. So in this time, you have to somehow have a component which really like decides on the new structure. So you not only have to predict your content, but also the structure wise. And the most common way of predicting a structure is the autoregressive one, where you again do this step by step and always predict, is this the next good way, or should I predict, should I stop my generation process? In all of them, of course, for each element of your output structure, we have a fixed number of vector, like the fixed vector. So the output is always the same, because you again do this thing that you just apply each one at each position. The other thing you can also do is like, instead of predicting directly your output, you're only predicting if two things are the same. So you put in two elements, two input structures, and you're predicting whether they are similar or not, in order to like then use them, for example, for finding similar elements. Good. So this is a bit the summary on the mappings before we are now looking in the last step on the data on which we are training them. Do you have any more questions? Yes? Yes, so we are not really doing any class prediction in that. So the only thing we're doing here is comparison. And the idea is by finding the most comparable class, that is also giving us a bit of a probability what is the best output. So you're modeling then your possible outputs no longer by your output layer, but instead by the pool of elements you're comparing to. So you cannot, I mean, the easiest way of doing that then as a classification is that you're putting in all your classes you have, you put one or several examples in there, and you're comparing them to all of them, and then you're saying the class that I'm predicting is the one which is nearest to them. You can, of course, then have their extensions to that you say, oh, but I can also detect out of distribution errors, so that there's no class fitting by saying if the distance is too far, and so no class of the predefined classes are fitting to that. Good. So then we wanted to, I mean, the last slides are about on which type of data you can train your network. And I'll not cover all examples here, but like some of the basic or important. I mean, the most common one is here, the supervised training. So the idea is you have your input and you have you predict your output, you compare your output to the reference, and this is what is done in most of current applications of deep learning. However, it of course might not be always that you have this type of data. One way of doing it differently is what we mentioned before, like self-supervised learning. So where the main idea is, oh, if we don't have the labels, we try to extract or remove some part of your input and do this as our prediction task. So you create artificially a new task which does it. But then from a learning perspective of how we are having our network architecture, it's still one which does exactly the type of supervised learning. Yes? And no, it's not really, it's more like you remove information from your input and predict this one. So for text, it can be you remove the last word and you predict the last word then. For vision, it can be you remove one part of the image and you're predicting then this part of the image. There's other ways of how you can deal with unlabeled data. There's a lot of work on this type of autoencoding. So another way, if you don't have labeled data, but you want to learn some type, a good representation in a supervised fashion, is to build a network which predicts the input again. Of course, this task, if you take the standard neural network, this task is too easy because, I mean, it's easy to just predict what you have as an input. So you have to somehow make this task more challenging and somehow add something so that it's not easy to predict the task. In the self-supervised learning, you throw away some part, and that is. There's other ways of doing. Do you have any idea in autoencoding how you could do that? What you could do with your input in order to to make this task interesting and it's not too easy to do the full prediction. Any idea? I mean, one way you can do is like do it as a compression task. So if in between the capability of your model is smaller, then the representation you have to learn has to be somehow meaningful that you can like grab as much information in there. So that is one task in an autoencoder, by have in between somehow a bottleneck, like a very small representation, so that you then have to like somehow learn which information are here somehow redundant in there and learn a good representation. The other way of doing is noise. So you're not putting in the real image here, but you put a blurry image or like half is black and white, and then you try to do the prediction task. Then it's of course also difficult because you somehow have to reconstruct that, and you have to learn the difference between that in order to do a good type of prediction in there. Then there is one other type if we don't have the right data to learn alone way, and that is what people refer to as generative adversarial networks. And here the idea is, so when do you apply them typically? So just imagine you want to generate an image and you want to learn to generate a realistic image of a human. You can, of course, give a lot of examples and you say, like, generate this human and this. However, it's very difficult to tell. I mean, we're good at learning like from discrimination. So good to learn from this is a real image and this is a bad image. But how do you want to tell the system, oh, these are all not images of human? There's a lot of ways how you cannot create a human. And it's not easy to tell the system with examples, oh, these are all bad images of humans. So therefore, the idea in generative adversarial network is, okay, let's also do this by a network. And we make this task of generating good images as a task. How can we do that? We have two components, the generator and the discriminator. So the generator has to generate random images of humans. And how do we know whether this is a good generator? If we put our generated images and our real images of a human and we train a classifier, then we have trained a classifier, we can do that. And this should classify this is a fake image or this is a good image. So now these two components, they play against each other. So the discriminator tries to discriminate real and fake images. And when we're training him, we're trying to make him as good as possible. On the other hand, the discriminator is trained in the other way. It's trying to learn an image here where the discriminator cannot do that anymore. So can you generate images where the discriminator cannot distinguish anymore between a real image and a fake image? And that is then, of course, I mean, if you train them one by one, hope at some point you have good images here. So you have a generator which can generate nice images of a human because the model up there told him, and with backpropagation, this is one large network again, you can tell the model like how to generate images which are then, most human-like, so that the upper model hopefully can't do that. And so you address here the data problem that it's like nearly impossible to get all images which are like non-human, because the model will then easily learn again these type of loopholes where it's like, yeah, in all of the data, sure, on no image looked like this, so it will just always generate this type of image or something, because you haven't told him what are all possibilities of not generating a human. I mean, of course, just having a model which generates from noise humans might not be super helpful. More interesting if you have then the conditional GAN, where you said, oh, it shouldn't generate something unconditioned, but it should generate something based on this class. So if you want to then tell the model generate a human, you put in here class human. If you want to generate a dog, it will generate a dog, and so on. So you can the model to really do something useful. And then you're comparing your example of the class with what you generated. And you again have this game of, can the discriminator generate, like, no longer discriminate them? So can the generator build good enough images so that the discriminator cannot disambiguate them anymore? This is, of course, especially interesting in more like vision tasks where you have continuous output, because there you can't do that. So some examples of that here. So this is like a conditional one. So just imagine you have an input, a segmentation, and you want to generate a real image out of that. Or you have this aerial and you want to generate that. So how do you train now the generator based on that? The left one is mainly your class. Then you have your image, the real image. You let the generator generate another image. And then you're comparing, like, how similar is my generated image to the real one we had. And your aim is that the generated image is so similar to this one that the discriminator can no longer like disambiguate that. Or like this could be the other one. This is your class or your input. Then your generator will generate an image based on that one. And then you compare these two by the discriminator. And during training, the discriminator tries to discriminate these two, and the generator tries to learn a model that it's impossible or like very difficult to disambiguate these two types of models. Yes? It's like for the conditional generator. So you put also the condition on what it should generate something. So based on noise on the condition, you generate then something like. Yes, or the back. I mean, how you exactly do that in the network is again based on the structure, how you put in the image in there, but you can't put it in there. Yes. Good. So to summarize what we should have seen today in this service, you should remember the three main components of different types of models, because again, think of this. I mean, if you get the task of, okay, I have to build a model on that, you have to think, what is my task? How does my input look like? Based on your input, is it like a sequence? Is it an array, or is it like a graph? You have to select what to do that. Then you have to check what is my mapping. Based on the mapping, you can decide what type of layers you have, and based on your data. So these are the three main things you should consider when you design your network architecture. And what type of components you can use then to implement different types of, we look into then next week. And on Thursday, we'll have the first practical one where we go a step back and you look at the standard feed-forward neural network to do that. Thanks.